So, welcome to our current lecture on AI. Today's topic will be so-called classical planning or automated planning, actually a part of automated planning, where we'll basically be looking at a formal way, like a standard way of describing some problem, basically, and then how to solve it, basically. How to, in a discrete, deterministic environment, meaning it's a simple world. We'll be talking about simple worlds where everything is known, where all steps are discrete, and we know everything. Fully observable environment, meaning we know all the facts, right? Again, there are problems where we don't know everything, right? Where we don't have where our moves are not discrete, where we have a floating point moves, right? Where we don't have a step, right? And also where we have probabilistic moves. So this is so-called classical planning. A lot of research has been done on it, actually, for last 50 years. So relatively well studied problem, a well-known problem. Not, of course, also sometimes even with all the knowledge, of course, there are subclasses of this, which are not trivially solvable. But another thing I want to talk about before we go to the topic of this, about actually the midterm, or maybe lack of midterm. But I have an idea, right? No, don't be too happy, because no, here's what I have in mind. I have in mind a slightly more challenging second homework, right? Meaning, I'll tell you what I have in mind. It's on Thursday I should have exact specification. It's a adversarial game playing, meaning a game bot, right? So there will be a simple game, right? But here's where the challenge comes. It's sort of like technical part. All of your submissions to get a good grade will have to be required to use a specific type of API, meaning it's some sort of JSON type of API, very simple one, right? Because why? On a day of midterm, we'll run a tournament. What do you think?
So if you lose your...
No, so idea is this. So here's my grading idea. So if your program runs, with this API, you'll get 7, right? If you have completely random, if you have completely no strategy, right? It just runs. It's really stupid, right? But it runs.
So runs equals...
makes legal moves.
Oh.
Yeah.
So it's not that runs equals not crash.
Yeah, that's also a good sign if it doesn't crash. But so I'll be more I mean, if it crashes occasionally or if it loops too much, because what I'll be doing, it's going to be a simple game, most likely something NIM based, because I don't want you to, not too hard. So, but still, I want to leave you how should I say, room for error, right? To make things, not to be too trivial, right? So there'll be different type of solutions possible. So where's the fun part? My fun part is, in terms of midterm, we basically run the programs and see who the winner is, right? So that's the basic idea.
So the winner gets 10.
Of course, right, obviously. But even, there should be, I'll probably give you a couple tens, right? There'll be room also if you have a really good program. It should be, it doesn't win. Maybe it only comes like second to last, but has some really good ideas. You can still get 9 or maybe even 10, right? So 10 maybe not, but 9 for sure. So again, if it just runs 7, right? So
only 110 will be given.
No, I'm not such a hard-nosed, right? So no. I think couple 10s, plenty of 9s, right? Room for 9s and 8s, right? So that's the idea. So of course it's extra work for me because I have to set up a server, right? So that's what I have to do, right? Of course I could, automatic 10 for who writes a server for me, right? But no, right? Yeah, right. So in fact, it's not so hard. It's just time, right? So, but yeah. So that's the idea. What do you think of this idea? Yeah, it's more interesting, I think. Yeah, okay, so time-wise. Okay, so when do we want to do it? So I'll tell you where we don't want to do it. We don't want to do it in 2 weeks, 24th, because some of you are taking programming languages and you'll have a real midterm then, right? So 24th, no. So my thinking is 27th, that's 2.5 weeks. That's doable, that works for you guys?
If we get all the details.
Yeah, so on Thursday we get all the details, like I said. So it should be it's basically two parts, right? So what I'll do is, if you for some reason, I mean, it's not that hard to make it, you know, to do it. I don't. I mean, it's like I'm biased, right? Because so since I have an idea, right? But I also want to leave it open-ended. So we're talking about the midterm or the lack of midterm, right? Tournament. On 27th there will be a tournament, right? So yes. Because the alternative is midterm, where you have to code something on you know, during the class, and it's more challenging, I think, and more stressful, I think, for some people, right? And again, the thing is, again, so there'll be, so I have to think how to give you less than 7 for those who maybe don't get the API, doesn't work, or they maybe using language doesn't have good network libraries or something, I don't know, right? So I'll probably offer it, right? I mean, you're free to use any language, right? As usual. In my course, in AI course, right? For this, you can use any language: Python, Go, Java, C++, whatever you want to use, right? PHP, whatever, right? So, okay, so that's the idea. Are you pretty much all on board on this, right? Okay.
Yeah, but what happens to the grading?
Excuse me?
What happens to the grading?
Okay, so grading, okay. So I still don't, you see, I don't want to be, okay, no, you know, I don't want to be like first 3 players get 10 automatically, right? That would not be.
I mean about the semester grading.
Okay, this will count as a midterm, basically, right? Yeah, this will be the midterm, right?
When will you publish?
On Thursday. I have a good idea, but like I said, it's probably going to be something like NIM, right? Probably, right? I actually had 2 ideas. One was Connect 5 or NIM. Connect 5 maybe. Connect 5 is kind of fun, right? But that's hard. I think it's hard there. You know what Connect 5 is? It's like DESAS, TKF Piets.
Oh yeah.
Yeah, you probably played it, you know, on a piece of paper, right? Do you want, okay, so, or maybe, well, no, there's one problem, but we don't actually want a tournament, then it's no fun, right? So one problem. So, Connect 5 or NIM. You know what NIM is? Very simple game. Really simple. I'll show you what NIM is. NIM is like the very basic game, but I'll have to modify, not the programming language, it's a game actually, right? There's also programming language. You can use NIM to program RIM, right? So it's like this match game. Yeah. NIM is actually kind of fun language, by the way. It's kind of like Python but compiled. Yeah. So, but yeah, this is like the world's oldest game. That's why I'm kind of partial to it. It's like supposedly the people in cavemen played this game, right? So on cavewoman, right? So there is the thing is, okay. So if you do some research, you can come up with optimal strategy, right? That's the thing about this, right? So I have to make it a little bit harder so it's not completely easy. Everybody makes perfect strategy, and then everybody gets a tie, right? And then it's, yeah. Okay, there's 2 ways. So basically, usually the last player to take a match loses. That's the rule, right? The loser is the last person, and you can take basically a certain number of matches, maybe 4 or 5, up to like some number of matches, right? Each turn. 2 players, right? And last player loses. Last player has something to take, right? Last match, right? They lose. So you have 2 matches. One player takes 1, second player loses, right? If you have 3 matches, right? The second player will take 2 matches off, if it's allowed, right? And the second player, then the other player loses again, right?
And what determines how many matches are you allowed to take?
Well, there are different rules, right? So different versions of the players. So usually I think it was 3, right? 3 of them, right? Misère game, like that means the last player to lose, right? So, but there's a rule, right? I think it used to be how many? Let me see. At least 1, okay. Yeah. So there's mathematical theory for this actually, right? So it's like basically, I don't want to give you too much, away. So that's the thing is, I'll have to modify it a little bit, right? But it's simple, but the good news is it's simple to program, right? It's pretty simple to program, the basics. So 7 should be really easy to get, right? To make it play, right? To make a move, right? to play and lose, right? Losing strategy, right? So how about so again? So that's what I'm saying. So this name maybe Connect 5 or maybe no something more complex. I don't know. Connect 5 would be more fun actually. I think because then you have actual gameplay. We could see it actually.
There seems more variation.
Yeah. So I think Connect 5 is more maybe like it. And that will make it more interesting, very wide, be very wide open. So basically like you can think of it like a super DASs basically. All right. Okay. All right. So Thursday we decide on Thursday, right? Well, all this stuff. The basic idea you understand the basic idea, right?
Which Thursday?
This Thursday.
Oh, okay.
This Thursday we'll have the definition, right? Okay. All right.
What exactly is Connect 5?
DASs, you mean like tic-tac-toe?
Just
Just 5. You have bigger board.
Okay.
Yeah, so we can do the research. You can do it for Connect 5, right? Right? You can play it here. Right? Here you go. Right. Oh, but this, of course, I don't know. Okay, but this is like the version with there's like turns. There's extra, you probably have a children's game at home somewhere, right?
But isn't it Connect?
The-
Okay, it's Connect 4 but bigger.
Yeah. Yeah. 5 line. Because you can do diagonals, right? So we got to block it, right? All right? All right. Let's see, do I lose? I think I'm going to win, right? No, I have to be careful now.
you can diagonal.
Yeah. No, okay, see, this guy is kind of there. Okay. What?
Did you
I-
press?
Oh, right, because this is, no, I see. Yeah, this actually is called 5. This is the actual, this is different, a little bit different. This is actually the version, you see, I can't put, he cannot win. I mean, this is, if I put here red, he's going to put, the computer is going to put here, right?
Yeah.
And I lose, right? So, but yeah, I haven't played this in a long time, right?
Why did he not?
Because he cannot, if he puts blue here, I'll put red and block him.
Oh, yeah.
Right? So you want to go in the Zugzwang, right? You want to make the other player play. So let me see how I can do anything. Yeah. Okay. So this is good.
Block him.
Where?
When you just talked about.
Oh, here. You're right. I'm completely sorry. Okay, but look at this now. I should win. Right? I have 4, 4, 4. Right? So if he puts a piece here or piece here, he loses. Right? Correct? So I should start putting something here. Well, no, he's running out of space. So what I should do is I should put everything else. Okay, these are useless for him because I'm going to be first, right? So let me finish this, or I'll probably lose something. Okay, no, I don't want to do that. All right, that doesn't matter, right? I'll put here. All right. Okay, no. Oh, let's see. 1, 2, 3, 4, 5. No, okay. Those are kind of dangerous, but okay. But it's never going to get that far, right? I hope. I don't know. I haven't played this game in a long time. Maybe I'll lose there. Okay. Oh, I have double win. I have win here, you see? Do you see the win? Because if I go here, he has to go here, and then I can go here. Yeah. There you go. No, what the heck? Okay, yeah. I win.
So can we call this website in the background?
Yeah, and then you just basically screen scrape, right? Screen scrape on the solution. So yeah, something like that, right? Except this is a version which you have the extra challenge, right? I think this is a little bit hard to program because you have the extra move. You cannot put anywhere, right? I had in mind the basic version, really simple version where you can put anywhere on the board, right? Maybe it makes things all build draws, maybe, right? Right? But it's simpler to program, slightly, right? But this is kind of fun, right? Diagonal, because scoring is easy, right? I mean, programming wise is easy. It's just coming up with strategy is a little bit harder, right? A little bit harder. All right. So that's I think this is more interesting, right? Especially if I'll provide an update how the game goes, right? So that will be interesting. right? So you know, I think this is pretty doable. What do you think? Yeah. Okay.
Wait, it will be this or like we have 19 by 19?
I was thinking more like the basic version, 19 by 19 with anything. This is a little bit harder to make, right? So let's make it, because I want to call it more not the rules, you know, the tricky part, the actual gameplay itself, like, you know, some strategies and things like that, right? Here you can get messed up. Maybe you make some, you know, illegal moves. Like, you know, I want to move towards like, you know, like how in, well, for example, Go, right? Go would be very, well, Go would give it to you very wide, you know, very hard program, right? A good Go player, right? You need a neural net, right? To be a good, right? So, no, for now I want something relatively simple, something which can have some brute force, some search, some tree search maybe, you know, something simple. Okay. All right, let's go to the topic. Today is relatively, I would say, probably the most, I wouldn't say most boring topic, but kind of like, well, it's sort of like something that the AI book has to include a full, but it's not really, it's sort of like limited, I don't know how useful it is basically. So because we're going to be talking about something called planning domain definition language, basically. It's kind of based on Lisp, basically. Right, sort of looks like Lisp a little bit. Let me see. I'm not surprised it's all in my notebooks. My notes for this are come on. All right. Right, so basically, of course, again, so planning means we have a plan of action, right? We have some problem, we have some goal, and all of this here is sort of like to come up with some just general, like a specific, like a domain-independent way of setting up. So it would work for any type of problem, right? Because remember last week you built your own semantic networks, you know, you have your own idea how to represent things. This is sort of like a, okay, set in stone, how to do classical, discrete, so these are things, discrete, deterministic, discrete, deterministic, right, on, completions, maybe oh, come on, I'm lazy, so, yeah, so deterministic, discrete, static, meaning no random gold appears, no random pieces appear on the board, right, and fully observable, we know everything, right, so you basically, kind of like in the chapter 3 when you had the shortest path, but that was very specific for the actual path finding, just general problem. And the idea was, okay, you set up all of this, you have the state, meaning all information, right? You have some things we can do, the moves, right? On initial state, where you are in the beginning, and the goal. So, and the big dream was, okay, this would solve all of the, you can take this sort of framework. It's like you can take a library, like a technique, right? And you can apply it to pretty much all the problems as long as they are, of course, discrete, deterministic, static, fully observable, right? So, again, later on in the course, we'll look at, of course, things which are uncertain, right? Dynamic and maybe they're probabilistic, right? So, air cargo transport, right? So, and again, we come up with this domain like there is a cargo inside the plane, right? Again, predicates, right? And denotes object X, right? It's at airport, right? At X something, plane or cargo is at airport A, right? So basically, of course, this means if you're going to do something like this, right? You have to keep track of these predicates, especially at predicates, right? Because, you know, if your plane is in, you think your plane is in, I don't know, Los Angeles and it's actually in San Francisco, right? You have a problem. So, yeah. So, there are no universal quantifications. So, it's like our previous lectures, we talked about the universal, you know, the first order logic and the predicate language, right? This is sort of like standardized, right? So, let's take a look at this example, right? So, you want to go from what? Problem would be go to get cargo, right? Plane 1 at San Francisco, right? And you fly a plane, right, to John F. JFK, right, unload. JFK is in New York, of course, right? So I think it's New York, right? Yeah. So unload cargo there, load cargo from C2, right? Fly back, and of course unload cargo. So fly, load, and load, right? Yeah. So simple problem. So basically this is a PDL language, right? So how about the spare? How would you spare this change a tire, right? You have a your car has a good flat tire. Well, and the thing is actually, of course, again, this book is from 2019, 2020, right? But now newer cars, there's a problem here, right? Remove flat, right? You remove the bad tire, remove the spare, put on a spare, right? And leave the car during night, right? And somebody steals all your 4 tires, right? But another thing, of course, if you think about it, right? Like off the side problem is that most modern cars don't have spare tire, right? Right? If you, but like at least last 5 years, many cars don't have spare tires. I don't know if you checked, right? Like they have that like spare tire kit, like you can like fix it or something, but they assume you're not going to fix the tire yourself. You're not going to change the tire. I don't know if you have checked the newer cars. Less cars. I'm kind of surprised actually about this, right? People are upset because people, I guess they save. And why is that the case? Because newer cars have to meet tougher emission standards, tougher mileage, right? You know, less. Taking off a spare tire from your trunk, right, and replacing it with some stupid glue or something, right, saves technically, you know, increase the mileage or kilometers, right, per liters. How many, lowers the how many liters per square kilometers, right? A little bit, but still noticeable. So kind of annoying side problem, right? But this assumes that you have a classical problem. You actually have a spare tire, right? You could add some joke steps here, but you don't have, right? So remove. These are actually actions, right? Remove, put on, right? So remove flat, remove spare, put on spare X, and that is it, right? Right. Leaving the car unattended overnight, right? Don't do that, right? Don't do that to drive home or get a tow service, right? So how many of you had flat tire? Whoa! I mean, on your own car. I mean, driving, right? Yeah.
I had it from like German, like auto plant.
Oh.
It wasn't fun.
No. How is it like America where you have to stop on the freeway and then you have to call the box or policeman will stop by immediately almost?
Well, our tire exploded. Like it was like just flat tire. It was like the whole rubber was just like hanging by.
Threads. Yeah.
And we stopped. We tried to call. It took like 20 minutes for the line to open.
Oh.
So when after that, like hour to wait.
And then they told you, right?
No, they just like we had.
Oh, you had spare.
We had spare, but we couldn't like take it off.
You didn't have the jack?
Yeah, but it was like so snug that we couldn't. So he helped us, and so we didn't have.
Okay, just one question. How much?
50.
Oh, that's cheap.
Yeah,
That's
we-
relatively cheap. See, that's one of those things like water bottle in desert. How much should it cost, right? Right? You probably were ready to pay more, right? Just get out of there. Right, so that's good. Maybe hopefully they have some sort of law which limits that, don't charge 200 euros for that, So yeah, so that's the problem. The thing is, the removes this flat, right? This is a step 1 problem actually, right? I have from experience too, right? If they put them at the service station, they change the tire, right? They have the automatic, what you call, the air pressure, they automatically tighten the screws, right? And then you try to do it and you can't. Yeah, so that's a problem, right? So yeah, okay. So yeah, this is again very abstract. It assumes you actually can do this, right? Remove the flat, right? But yeah, of course, the resulting solution would be. So the classical way is so-called block world, meaning they define this domain. This is like from again 1960s, 70s, which has some blocks, right? Like, I wouldn't say them Legos, more like, I don't know, who makes blocks? Like children's blocks, I guess, right? So, this is like the domain, right? You have blocks, cubes, maybe pyramids, right? And you can put, you have a robot, right? They had, even then they had robots even in the 70s, right? Which can make movements, right? Take single action, do something and put it somewhere, right? And the goal was to do something. Maybe put them all stack on top of each other, right? So they don't fall off, right? So, it's again a good for like, sort of like learning example. Something's on, right? There's a predicate, something's on top of something, right? Move, you have a treat move, b, x, y, right? You move something to x, y, right? And then you have also clear predicate might be useful to check if there's nothing on the board, right? Right. So this is the clear predicate, right? Maintaining this knowledge base, this database of knowledge state is not trivial when you're talking about checking whether something is clear or not, right? So whether actually, so they made some adjustments to this, right? So action, right? Move to table, right? But how to do this, right? And there's also interpretation of clear, right? So it implies the clear table is always true, right? So, and then you put something on there, right? So prevent this misuse of move, right? Block, right? There's also predicated block. B has to be a block, right? It's not just like a person or something, right? So the PDDL, let me see that if I can show you example. I had an example somewhere what it looks like actually, right? I have it somewhere. Well, I don't have it here. Let me see if I can do this here. Okay, yeah. Example PDDL file. Maybe AI can do this for me since I'm lazy. Example PDDL file. Example of problem file for block world. Yeah, it's in Lisp. You see, Lisp, which is closure, right? Something like this. Oh yeah, there we go, right? So you probably remember this, right? Some of you are could have recently. Some of them maybe from, right? Remember closure, right?
Yeah.
So that's Lisp, right?
The language where,
Yeah.
where someone got the code couldn't understand it.
Yeah.
Somebody,
Yeah. So you can see this certainly looks like Lisp. Let me enter, right? So you define problem, prob1, domain blocks, objects, ABC block, right? Init. So again, why they use Lisp-like syntax. So basic, of course, the idea being, so you can take, okay, this is technically a Lisp program, we can feed it into actual or machine, right? And it will give you the set of actions, basically, right? So this is how, this was serious research in 60s and 70s for this, right? Maybe it seems like, okay, this is the right direction, but this is needed, right? So you would do this, PDDL uses Lisp-like, program file, typically using PDDL, my problem, problem PDDL, right, type naming, right? Yeah. So PDDL files. So idea was, okay, you define it. It's because again, the advantage of this, of course, is Lisp syntax is very, you're not writing a full Lisp program, right? You're just defining the problem, right? Kind of like Prolog also, right? They didn't like Prolog, it was not that big. Lisp was bigger at the time. So you define this problem and then you feed it into the solver and you solve the problem basically, right? You have the goals, right? And again, just with the exception of the bunch of parentheses, it's pretty clear to come up with a syntax and define your own sort of problem. So how do you end this, right? Of course, right? When the goal is reached, of course, right? So again, how did they approach this? Classical algorithms, obviously the forward search, right? Kind of similar, kind of like matching in the predicate logic, right? You start from initial state, and then you keep looking. You have actions, right? And you try to move through the state space towards the goal, right? That's how you would try to do it in your real life yourself if you didn't know better approach, right? Very simple. You start at the beginning and try everything towards the end, right? Simple approach, right? Well, backward search, as we saw it also in our first order logic, solving our predicates, might be more efficient, right? Why? Because goal might be more clearly. We have better way of cutting off the bad state transitions because your potential moves is going to explode, right? We have a problem with exponential complexity, right? Your moves, potential moves, you have to look through, right? Brute force search is going to kill you, right? So, okay. So, translation to logic sentence, logical inference, right? So, that was the third approach, and that was probably the least intuitive, right? So, you have these action schemas, and you sort of convert them to logical sentences, right? And then you can use logical inference algorithms, right? So, kind of something we did in chapter 9, which is first order logic. So very deep, it's very closely related to that. So, okay, so forward state search, right? You have, right, something that's true or false, right? And goal state is defined by specific combination of truths, right? So actions, you know what we can do, right? So challenges is like this book, this is from the book, right? That the complexity explodes, basically, right? We don't have you need some sort of cheat codes, basically, right? But the idea was they hope to do this without knowing the specific problem, right? The idea was to have make a general solver, GAI, right? General AI, which we still hope we don't have general AI, right? So, so domain specific, right? So idea was to develop strong domain independent heuristics. So what's heuristic? It's like a cheat code, like a rule. You know, see lion run, right? So, so here, yeah, that's a heuristic, a pretty good heuristic, right? Yeah.
Your chances of surviving.
Yeah, no, you have to, what's the joke about, that joke about the two guys, right?
You don't have to outrun.
Yes, the bear.
Outrun the next one.
Yes. So that's the thing, you might as well start running, right? Yes. So, right, so the thing is, the hope was, right, that there are some heuristics you can develop, you know, some cheat codes, basically, which don't care about what kind of problem you're solving, whether you're changing a tire, whether you're flying an airplane, right, whether you're moving a blocks, that this is going to somehow help you cut the search space, right? So, pretty powerful, right? What's the other approach? Backward search, right? Regression. You start with the solution. All right, we already have put the blocks, we have already changed the tire, right? So you go backwards. You go backwards from this, right? And you connect eventually. The hope is that, well, this will be less, right? Of course, also if you think about, okay, forward search, backward search, maybe there's room to do it in both ways, right? Middle out algorithm, right? Start from both ways and meet in the middle somehow, maybe, right? That might be an approach as well, right? So, yeah, so you regress. So, of course, this means when you're doing sort of regressive planning, right? You probably need to account for some new variables, right? There's some new goals, these intermediate goals in between. So it can be more efficient, right? With when you have many possible actions, right? You will be able to use this branching factor. So that's good, right? So, but again, but the book says that the effective heuristics, effective rules, effective line rules, you know, I'm saying, you know, this actually, it's simpler, basically it's simpler to make forward search, basically, right? So, right, so, let's see, maybe, oh, there's a book, ISBN, let's say you have an ISBN, let's look at the book example, let me see if I have it here somewhere. ISBN, do I have it? ISBN? I don't know where I have it. Okay, yeah. Oh, this is an example, right? So, backward search would be for searching for, okay, so, you have a goal of owning book with certain numbers, right? You know, like ISBN is a unique identifier for a book, right? Like 13 digits, I believe, right? And, you know, like, let me show you, right? If you go to Amazon, let's see, AI Modern Approach, this book, Modern Approach, Amazon, right? And we go here, right? Oh my God, this looks, you see, that's, I hate when you're doing anonymous browsing is a pain because it doesn't, almost nobody likes you then, right? So this code, right? This is 3, oh, this is 10-digit ISBN, right? God, they increased the price? 225? Jeez. That's a lot of money. Yeah. Yeah, I don't know anything about flying some flags, you know, the Jolly Rogers, right? So, yeah. Yeah. No, okay, but yeah. What I was going to say is this, right? So this now, so the goal is to own this book, particular book, right? So, so you have trillion digits, right? So if you would start enumerating from forward search, it would be silly, really, right? But if you're going backwards, it would be trivial to unify the goal. So if you saw this again, we were talking about Prolog in programming language today, right? It's kind of like which way you look, right? Whether you have a predicate 5 is equal to 2 plus 3, right? X is equal to y plus 3. If you go one way, it's trivial to solve. The other way is pretty hard, actually, right? Because finding for AI, for people, we know the formula, right? We know to go reverse, we take -3, right? And it's solved, right? But in general, in many cases, going one way is much easier. Like in some case, it's impossible to go backwards. Hash keys, right? Cryptographic keys, right? Going one way is easy, right? You just do some actions. Backwards, impossible, right? Well, near impossible, right? You don't know, right? That's part of cryptography, right? For coming up with good one-way algorithms, right? One way is easy, other way almost impossible, right? So, okay. So yeah, so that's the issue, right? Sometimes, in general, we don't know, right? Which way is going to be better? So you probably try both, right? So on the third approach, again, this is the third approach. I don't really. It's harder to follow, which is basically the Boolean satisfiability. You convert this problem into this Boolean satisfiability problem.
Yeah.
SAT problem. I call them SAT problems, right? And of course, for me, actually, by the way, SAT has two meanings, right? In America, SAT is like the test you take in high school. So, right? So it's kind of it has two different meanings in my mind. So, but SAT, let's call them SATs, right? So SAT here means a different thing. It's a satisfiability problem, right? So you convert it. Excuse me? Oh no. So it's basically, you say, okay, you convert this problem to a different problem and let the SAT solvers solve it for you. Unfortunately, that doesn't really solve it for you because it's a NP hard problem, right? NP complete, I believe. Yeah, NP hard, right? So exponential problem in general, right? So what other? Okay, so let's think about some other plans. What else could we do? Yeah, the first, forward, backward. We convert to this Boolean satisfiability problem, right? Meaning you have a bunch of statements, and say whether this is true. Graph plan, meaning you have a data structure, sort of like come up with a graph plan. Maybe I'll show you what it looks like. Let me see what it look like. Graph plan, right? So you basically, I want to see what it looks like, right? This is like 1995, right? There was an AI algorithm. I want to see, there's Java or C++, but I want to see what it looks like. But basically, I think it is AI, right? This is, where's the graph plan? I want to see this one show. Yeah, what it looks like. It's from MIT. Open cursor, right? But this is, what's the point of graph plan if you don't see a graph? But it's kind of ugly looking, right? You have plan graph, right? Bunch of levels, right? And basically, start somewhere, right? And you want to have a goal state, basically, right? So sort of like some graph algorithms can be used, right? Looks like this. I was hoping for something a little bit nicer looking, actually, right? That's not very illustrative. Okay, maybe I'll leave a note. I'll leave a note for this, actually, right? See more on graph plan oh yeah, graph on also on MIT OCV. And no, let me see here. Let me see here. Yeah, all right. Can we do this? It looks like. Oh yeah. All right. So there's other approaches, something called situation calculus, right? Different formalism, right? And now to describe these successor states, right? How do you move from one another? Again, we can do a constraint satisfaction problems, right? Partial order problems, right? Again, as a graph, right? So, because of course, not everything, right, is linear, right? The graph, I like the idea of moving a graph, right? Representing a problem as graph, because it's more sort of like your movement from start somewhere is not necessarily just linear, right? You move into this non-linear two-dimensional, three-dimensional, or even multi-dimensional space, right? So this used to be kind of superior, right, forward, but basically it turns out, yeah, the forward search planners sort of like have taken over for this, right? So for example, yeah, the example, real-life example, so you say, okay, where is this useful, right? So Mars rovers, right, they're still running around. Is any of them alive still? Anyone know?
Yeah, I think so.
I think one of them,
Certain places.
yeah. So yeah, so they use that basically, of course, to facilitate the human oversight before the, you run it, right? Mars rovers employ some things that they have to go somewhere, right? And then of course they still use the human oversight to plan, right, afterwards, right? So the rules, the cheat codes, right? So what kind of cheat codes can we use for all of this, right? We have the general problem, right? So the basic idea, which is seen in algorithms course, right, which some of you have not taken, right? The algorithms course, the idea was relaxing the problem to something easier, right? And then you use that as a cheat code. That's a very good general approach, right? So admissible heuristics, right? You say, what happens if we make it easier? Maybe we say, okay, we want to navigate through a city, right? And we say, okay, what will happen if you have flying allowed, right? That would be the most efficient. We have a jetpack, right? We can go straight line, right? And that would be a relaxed version of the problem. Everybody has jetpacks, right? So, so we can add more actions, right? Add edges in a graph. If you think about it, if you have a problem as a graph, right? You can add some cheat codes, right? Or maybe you abstract the state space to reduce number, right? So one general heuristic is ignore, you have some problem, but you ignore all the precognitions, meaning you allow every possible move, right? It's like, so it implies that you can do everything instantly, right? Sort of like a super cheat code, right? So every action, at every situation, you can make any move. That's like, seems like maybe too relaxing, right? But yeah, so another thing is ignore delete lists, right? Meaning we remove the delete actions of negative literals, meaning we prevent some action to stop another action's progress, basically, right? So it seems like you're moving forward, right? So sort of like, we can use something like hill climbing, which is basically, you look at the gradient and you keep going, right? So those are like very general heuristics, right? So, and again, maybe we can do some pruning, right? Pruning is very good. If you have a big search tree, right? Somehow prove it, right? So, very useful idea, right? One idea, if you do, how are you going to prune? Probably have a bunch of search tree, right? You look for symmetry, right? You want to identify the symmetrical solutions, right? So you see, okay, these are, you have two trees, you don't need, doesn't matter if you go left or right, it's the same road which goes to the other it's symmetrical move, basically, right? So forward pruning, right? So that's a riskier one. basically you move onto most promising branches, right? You have preferred actions, like the more preferred moves, right? And that would give you like a sort of like, shows what's possible, right? Basically, right? So, so again, yeah, Deep Space One apparently also used this, right? So turns out this is an interesting example actually of Deep Space One, that some things, by identifying which things you could be serial, what does it mean serializable, meaning in order, like linear order, right? It goes one, right? One after each other. Before, if you had to look at 6 different things at once, right? It's much easier if you look at 6 things in an order, 1, 2, 3, 4, 5, 6, right? Because it's, it doesn't matter if you do 6 things at once or if you identify which can be done in a linear fashion, right? You replace the search space from 6 things to do. We just say, okay, they'll do these 6 things. Doesn't matter what order, they'll just do these 6 things, right? And that, of course, reduces the factor. Branching factor is reduced, right? So sort of like local improvements, right? And then your search space is much improved. I don't know, Deep Space One. Let me see where is it now? It's where is it? Is it still alive? Deep Space One is right. It was, and so it's gone. Oh yeah. This is when did it die? When did it go down? Right. Oh, it was for asteroid, right? So it was when it had ion thrusters. Cool. Right. It almost got to the comet, right? Deep Space One was kind of cool. Pretty small. So where is it? It's still around, right?
No, you said 3 years and something.
Yeah. Well, deactivated, but how was deactivated? Let me see. Mission overview results. They got by Mars, of course, right?
Current status.
Yeah, current status. What is it? All right. Okay. I told you it's still there. It's out there. It remains within solar system in orbit around the sun. So the question is how you're going to find it, right? Probably not a trivial task, right? Finding it if it has no communications. Sometimes some things come back. Like I think it's Voyager, which comes back. Like I think came back. I think, or one of the really long old ones came back, meaning they got the batteries again, right? Like they got some more energy, right? So, all right. So it's technically, well, it's gone, it's dead, but it's still around. Well, that's the theory. Okay, so let's look at this here. Let's add a link to this. Yeah. All right, we're almost finished. Actually, this is going early today. So, state abstraction, right? So, next step, right? State abstraction. Basically, we can try to simplify these complex problems by reducing the number of states, right? So basically, we try to reduce, we ignore some certain things, right? So what can we ignore, basically? Well, unfortunately, I don't have any good examples here how you would ignore something, right? But the part of how it's done is usually by decomposition, right? Define independent subgoals, right? So if you can solve divide and conquer approach, basically, right? You solve the problem, right? Smaller subproblems, and of course that assumes that each sub-goal is independent, right? So it would not work if you have a sub-goal, but it depends on something else, right? So this could be optimistic, right? So again, so one thing that I've done is another approach, of course, use something called pattern database. So you build up, you cache, you build sort of these previous solutions, sort of a pattern database of what can be done efficiently, right? So you pay it forward, you pay expensive computational cost now, and then you get it back later when it's quick. So like indexing. So think of it like indexing a database or having a hash table of some solution. You basically put them in, right? And then you get back, hopefully, you get back quick results, right? Quicker results. But that's it's very abstract. This works for pretty much any type of problem. That's the idea, right? That is the idea, right? So one of the overreaching themes in AI in general is that eventually these general solutions overtake domain specific. However, in the short term, right, domain specific, like domain specific is how to park a car on the street. Very specific, how to park a car on the street on Skola Siela, right? Very specific problem, right? And you could, of course, come up with some rules, right, for that particular problem, right? However, the idea is that eventually the general solutions will win out over these very specific. But in short-term one, might be easier to say, okay, yeah, my parking problem for this specific tree, I have specific, constraints, I have specific rules, I can, it's easier to solve the specific one. But the big gains come from these general solvers, of course, right? So eventually everything will be done by these solvers, hopefully, right? So, yeah, vacations, so applications, vacation planning, right? And so complex software also, right? Hierarchy, right? You break down things, subroutines, classes, of course, when you do your program planning, right? So, high-level actions, right? It's another formalism, right? Like another approach how to write down the problem, right? So, how to solve a problem by breaking it down in smaller actions, right? Again, you start with some primitives. I mean, nothing. It seems like a basic, basic idea. Start with some primitives. You have these high-level actions, right? More complex ones, right? So go to San Francisco Airport, right? Obviously, the high-level action. It's not really. It's too complex, right? So you need to, of course, say, okay, what's driving, ride-hailing, how you do it, right? So, and then might be refinements, there's implementations, and then you achieve the goal. And again, none of these approaches were, as you can see, right, none of them were winners, right? They are just part of your tools that if you want to say, okay, yeah, you can use that, right? So if you have properly defined high-level actions, right, then you have the goal is you end up with linear problem, right? You just say, okay, one step, another step, everything, one step leads to another step, and you have solved the problem. Unfortunately, of course, the problem, then you reduce the problem to creating these high-level actions, right? How do you compress, complex set of actions into one high-level action, right? So, and again, and then the goal idea is there are a bunch of these different planning tools. Again, why is this? This is a very active number of research, and it's still research, right? It used to be like the main area of research in AI, basically, because until, in AI winter, right? During winter, all the AI researchers moved on to these planning concepts because that's where money is, right? Logistics, huge area for this, right? Business in general, right? Multi-billion area of improvement, right? So, yeah. So one's approach is to keep replacing high-level action with the refinement. Again, now, what else? So primitive solutions, you can look for primitives, right? You break down HLL, right? That would be another approach, right? You have a high-level action, right? And you keep recursively breaking it down. So it's just like divide and conquer approach, yeah, right? It's kind of like what all the life coaches say, right? How you should do it. Like you break down a big problem, how to write a game bot, right? And you break down smaller steps, right? How do you divide? Okay, I'll write an API, right? I'll write interface, right? I'll write a little function which gives you the moves, right? And you break that function down into smaller functions, of course, right? That's basic programming as well, right? So, I mean, pretty much anything, right? How to finish college, right? University, right? You take classes and you get classes, you go to class and so on and so on and so on. Okay, but right. Maybe not very, no, but it's a decent analogy, right? So, abstract solutions, right? Okay. Right. So, I wonder why I made this picture. I'm trying to remember why I did this picture. And to what does it apply, right? So, high-level plans, right? So, the challenge, right, is how to determine these high-level plans, right? And also at the same time, keep, right, you have to, I know, right, there's angelic search. Where is, here, yeah, angelic search, okay. Yeah, we're going to talk about angelic semantics, right? So, very interesting theme, angelic search, right? So, basic idea is that our angelics, it can look for the best solution, right? Ignoring the devil, right? So things which can be done, right? Basically, right? So it looks for there's like an underlying idea, or I wouldn't say Platonic idea, but that this agent can choose the outcome of HLA, which will be more versatile than without reaching this. So, all right. So, where's my angelic search? Right. So, right. So there's two. Yeah. So this is a demonic non-determinism, where the bad guy gives you choice, makes a choice for you, right? Angelic is where you get to make choices. So that's a language. So demonic meaning is the other player, right? He's the devil, right? And you are the angel in this case, right? Making choices. Okay, that's what I was going to say. Okay, yeah, angels versus demons. Very interesting picture here. All right, yeah. So now, how do we move on from this? Right, this is all deterministic so far, right? Moves, right? Moving on to this non-deterministic means is we'll have to worry about partially observable, right? Non-deterministic, and of course, possibly unknown environment. We don't have all the variables, right? So basically, then we'll have to move on to belief states. You'll have to have a level of certainty, add extra, or planners will have to worry about these beliefs, right? And also, of course, how do we add information to the schema, right? So basically, also we come up, then we also change our assumption that we don't have a closed world, right? But we have open world where things come in, right, are updated, right, and we have new, we have basically new challenges, right? So belief states, right? Now, last thing today I want to check is online planning. So, online planning. What is online planning? That is when things are updated live, right? Not you have things happening in real life, right? So. New information comes in, right? So you need some sort of monitoring, some sort of sensor update, right? Your agent has to update this knowledge, right? And basically, then you have to make new plans, right? Contingent plans, right? Plan B, Plan C, right? If things don't go well, right? Because again, this is sort of closer to real world where things happen, right? So adoption, right? So. And all these things, again, are used in modern things like, self-driving cars. Of course, again, each step, right, broken down, right? And you apply some of the tools, right, for solving it, right? So, what else, right? So, temporal planning, right? Again, we also, of course, could have some constraints, right? We may don't have unlimited gas mileage, right? We don't have unlimited electricity, right? Like your little bots don't have electricity, right? So that's also might need to be incorporated, right? So time, schedule, and resource. And of course, there is a critical path method, right? I'll show you that one, I think. Do I have it here? Critical path method. Critical path. So scheduling problems are very well known, right? When can you do it, right? When should you do it, right? To show you critical path. Critical path method, right? Yeah. Basically, critical path, not CPA, right? Certified Public Accountant, right? No, it's critical path analysis, right? It's an algorithm. How do you schedule things, right? You have 5 milestones, right? And there's 2 critical paths, right? B and C. Okay, B and C. What is critical? Oh, there are 2. B and C. Okay, that's one path. And A and D and F, right? So activity E Why is that subcritical? Ah, okay, I got you. Okay, so in this example, right? Very simple example, of course, right? You start here, right? The idea is that this takes 3 months, right? This takes 4 months, right? And this takes 3 months. So there's no way around it, right? The idea is that this is not critical. Why is not critical? Because you have a month's leeway. You have 1 month's window, right? You can move back and forth, right? So it's not crucial, right? You have to immediately start. But this has to be, if you want to, you can do this in 7 months, right? This can be done in 7 months. And this means that this task E can be done on months 4 or 3. Doesn't really matter too much, right? And maybe months 3.5, right? And then it will still be okay. So, right? It has a float. The idea of float, not the floating, not the number. Float in here means in project management. You guys are taking project management, right? Yeah. They talk about this? No? A float and Slack. You have this, okay. Yeah, you're still okay. I know. I heard. I don't know. I'm not gonna comment on that course. So, okay. But yeah, but it's all right. Now what else? What else? I think we're all reach conclusion. I know you guys. This is like not the most exciting chapter. So they're different. So the idea is they're different formal ways of specifying your problem. You have to recognize what kind of problem you have. Is it discrete? Is it deterministic? Do you have complete state? Do you know everything about this problem, right? If you do, that's fantastic. You fit into your planner, right? And there's lots of different systems now. So basically, you don't have to do anything. You just have to define the problem, and the solvers will solve it for you, right? So, unfortunately, it's not always so simple, right? There might be something, there might be some constraints, right? Maybe it's like you need to worry about these high-level actions. Maybe you have to break down more, right? And again, most likely, your problem is not going to be so simple. You'll have to start worrying about uncertainty, about stochastic, about probability, which is where all the modern AI research has gone. So let's see. Yeah, so next on Thursday, we'll start talking about how do you deal with this uncertainty. How do you deal with not knowing things for sure, right? Do you have a cavity? Do you have a toothache? Like what's causing? If you have a toothache, do you have a cavity? Maybe, maybe not, right? But that's on for Thursday. Okay. All right, there's some notes about this. If you're interested in this planning, again, I personally, the feeling I get, the book doesn't say this, right? But feeling I've gotten is it's sort of like now it's not the hotness. It's not currently in vogue, right? Not popular, but it's still. I mean, meaning it's not in the news. This part of AI research, but it's still around because it's already well settled, right? It's been 50, 60 years of research, so the tooling is very mature, right? It doesn't give you all the solutions, right? But, right? If you can fit your problem into some existing framework, right, you can solve it relatively painlessly, right? So, okay, it's 5:55. Well, I guess that's it for today, right? So next on Thursday, game, right? Mm-hmm. Right. Design. I mean, you don't have to do it. I have to do it. It's my homework. It's my homework. I have homework for Thursday to finish specification for the game for you guys, right? And then you can do it. Okay. All right? Yes. Any questions? No questions. Yeah. Jā,
bet es pieņemu, ka jūs par midterm runājāt.
Jā, es teicu, ka 20 pirms aptaujināšu ierakstu. Pagaidiet sekundi.